I'm going to go ahead and add in a picture, and we'll take a look at some plots. So before we add in the plots, I'm going to introduce another substitution that's going to make the math a little bit easier for us. And that is a bar, which we saw previously in the equation for b. We're going to say that equals to a times capital Omega squared. And that allows us to do a couple things. First of all, we'll rewrite our equation of motion, our forcing function, y dot or x dot 2 zeta omega n x dot plus omega n squared x. And that's going to equal a times omega squared sine of capital Omega times t plus theta. And that allows us to rewrite the equation b, which is the magnitude of x steady state, b sine capital T plus theta plus phi. B equals just the regular a over positive square root omega n over omega squared minus 1, and we will square that whole quantity plus 2 zeta omega n over capital Omega squared. So now we'll go ahead and add in these pictures with this new definition of a, and that's not a bar. So this first picture we see is the amplitude ratio b over a, which is here on the vertical axis here, versus capital Omega over omega n. So we're comparing ratios here, so we'll explore this just a little bit. So b over a, so we'll scroll back up here. That's if we divide a on over to the other side, and b is the output. And so when b over a is equal to 1, that means I'll use a different color here so we can see what I'm doing. When b over a is equal to 1, that means that the magnitude of the output is the exact same as the magnitude of the input. When b over a is greater than 1, that means that the output is bigger than the input, which is interesting for when we're talking about a building that is maybe experiencing an earthquake, or the Tacoma Narrows Bridge. They were operating in that regime where b over a is greater than 1. If b over a is less than 1, you're getting vibration suppression. There's an input, and the output is smaller than that input. On the horizontal axis here, if capital Omega over omega n equals 1, that means that the input frequency is equal to the natural frequency of the system. And if that ratio is greater than 1, that means you're operating faster than the natural frequency. And if you're operating below 1, you're operating slower than the natural frequency. You might notice that at or around the natural frequency, we get large humps or large spikes in the magnitude of the output. And each line is a different value of zeta here. So for some system with very low damping, zeta equals 0.01. You get this dashed line where with a massive peak right at the natural frequency. And the peak gets lower and lower, and it also shifts a little bit. You can see that right here for zeta equals 0.2, there is a peak, but it's not at exactly the natural frequency. It's at some omega tuned. So omega tuned is the input frequency that gets you the largest magnitude of response, and that equals omega n over the square root of 1 minus 2 zeta squared, which is approximately equal to omega n for small zeta. We'll go ahead and add in another plot. We're looking at very similar quantities. We have omega versus omega n on the horizontal axis, and we have that phase angle phi on the vertical axis here. So if we'll remember, our input was some sine of capital omega times t plus theta, and the output was some sine of capital omega t plus theta plus phi. So this phi is the plot that is what's being shown in this plot here, and it's the phase offset. So if we're vibrating at one frequency, if we're giving one vibration to an input, a phi of 0 means that when the input goes up, the output goes up. They're in phase with each other. A phase angle phi of 180 degrees means that when the input is going up, the output is going down. We're completely out of phase. And we can see that at low values of this ratio, omega over omega n, at low input frequencies, we're able to follow pretty closely in phase with the input. And then at the natural frequency, we drop off with varying steepnesses to being completely out of phase. And you can see with very low damping again, it's almost a vertical drop all the way down to, and it gets to negative 180 really quickly. And as zeta increases, that slope kind of eases off, and you spend a lot more time at intermediate phase offsets. We'll go ahead and finish that video here.